Hello everyone, in this mathematics, calculus and AP calculus tutorial we will learn how to solve integrals by substitution. More precisely, we will learn how to solve these three integrals. We will first solve these examples in order for students to obtain an intuitive understanding of integration by substitution. In the second part of this tutorial, we will explain a general approach for solving integrals by substitution, and we will give more complex examples. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let us first solve this integral. But before we start with this example, let me ask you the question. What is an integral? I will stop for 2 seconds, think about this question, and answer this question. Do you remember what is an integral? Well, an integral of some function is another function, I will denote it like this, g of x, such that when you take the derivative of g of x with respect to x, you should actually obtain the function under integration, and in our case, this is e to the power 5x. That is, we search for the function g of x such that when we take the derivative, we should obtain the function e5 of x. How to solve this integral? Well, do we know how to solve this integral? Yes, we know. The result is simply e to the power t, where t is a new variable. How can we verify that? Well, we can take the first derivative of e to the power t, and obviously we obtain e to the power t. Now here's the main question. Can we use this simple integral to solve this more complex integral? The answer is yes. The idea is to introduce a new variable t and to make the following substitution. T is equal to 5x. With the following idea. We know that, again, that e to the power t dt is actually equal to e to the power t. Now, the issue over here is that we can substitute 5x for t, and we obtain this expression. However, the problem is now dx. We cannot integrate e to the power t dx, since over here we don't have dt. So how to create dt over here? The main idea is to differentiate this expression with respect to x in order to obtain dx. So let's do that. We can write dt over dx is equal to, let's look at this function. The derivative of this function with respect to x is obviously 5. Okay, from this expression we obtain the following. We obtain that basically dt is equal to 5 dx. Or in other words, we have that dx is 1 over 5 dt. Now, let's substitute this value over here. And let's see what do we get. We get the following. We have an integral e to the power t. Then over here we have, instead of dx, 1 over 5 dt. Perfect. And as the result, we have 1 over 5 integral e to the power t dt. We can take 1 over 5 out of our integral since 1 over 5 is a constant. And do we know how to solve this integral? Yes, we know how to solve this integral. This integral is simply equal to 1 over 5 e to the power t. And let's perform back substitution. We know that t is actually 5x, and as the result we obtain that the integral is equal 1 over 5 e to the power 5x. Consequently, our integral, that is this integral over here, is 1 over 5 e to the power 5x. And that's it. But wait a second, how can we verify that this is the correct solution? Well, if we take the first derivative of this function, we should obtain e to the power 5x. So let's do that. d dx of 1 over 5 e to the power 5x is actually equal to, let's solve this. We have 1 over 5 multiplying what? E to the power 5x multiplying derivative of 5x is simply 5. And as the result, we actually obtain e to the power 5x. And that's it. We have correctly solved this integral. Perfect. Okay, let's now try to solve this integral. Let's see. We want to solve an integral of square root of 2x plus 2 dx. Let's think about it. How to solve this integral? What should be the substitution over here? We want to introduce a new variable t such that we can solve this integral. Here's the main idea for solving this integral. Do we know how to solve an integral of square root of t dt? Yes, we know how to solve this integral simply because we know how to solve the integral t to the power 1 over 2 dt, and this is basically a general form that looks like this, t to the power n dt, and we know how to solve this integral. So that's the motivation. We want to make this integral to look like this, and we can do this with the following substitution. T is equal to 2x plus 2. So let's write it down. Integral of square root of t dx. And again, here's the issue. We cannot integrate this integral simply because we don't have dt. So how to create dt? We'll take the first derivative of this expression. So we have dt over dx is equal to, let's see, we have 2 multiplying 1 plus 0, since the derivative of 2 is equal to 0. Consequently, from this expression, we obtain that dt is 2 dx, or from here, dx is 1 over 2 dt. Perfect. Let's substitute dx in this equation. As the result, we obtain square root of t, and instead of dx, we can write 1 over 2 dt. Since 1 over 2 is a constant, it goes out of the integral, and we have square root of t dt. This integral can be written as 1 over 2 integral of t to the power 1 over 2 dt. Now we have to remember the general formula for computing integrals of t to the power of something. Let's do that. T to the power of n is actually equal to t to the power n plus 1 divided by n plus 1. How do we know that this is correct? Well, if we take the derivative of this function, we should actually obtain t to the power n. And that's it. Okay, let us not confuse this formula with our original integral, so I will mark it like this, and let's continue. We have from here, I'm just continuing this expression over here, that this integral is equal to 1 over 2. Let's see what do we have over here. We have t to the power 1 over 2 plus 1 over 1 over 2 plus 1. And as the result, I obtain the following. I obtain 1 over 2, and let's see over here. I have 1 over 2 plus 1, that's actually 3 over 2. So I have in the denominator 3 over 2, and in the numerator I have t to the power 3 over 2. I will simply expand my screen and I will continue with this integral. I will continue over here. So we have 1 over 2. Let's fix this term. 3 over 2 is actually 2 over 3. Multiplying t to the power 3 over 2. And let's see the final result. So we obtain that the integral of square root of 2x plus 2 dx is actually equal to, let's see, 2 and 2 can be cancelled, and we have 1 over 3 multiplying. Instead of t, we can obviously write 2x plus 2 and the power is 3 over 2. And that's it. Now, how to verify that this is actually the correct solution? Well, we will take the derivative of this function. We want to compute d over dx of the function that looks like this. So let's do that. The derivative is obviously 1 over 3. Then I have 3 over 2 over here. Then what do I have over here? 2x plus 2. 3 over 2 minus 1 is 1/2. And then I need to take the derivative of 2x plus 2 times, I have over here, the derivative of 2x plus 2 is simply 2. And let's see the result. 3 and 3 can be cancelled, 2 and 2 can be cancelled. Consequently, I obtained square root of 2x plus 2. And that's exactly the expression under the integral. This means that we have correctly solved this integral. And finally, let's solve the third integral. How to solve this integral? In the sequel, I will show you that with the proper substitution, we will be able to transform this integral into this form. t to the power n dt, where n is an arbitrary number. And we know how to solve this integral. So let us wisely choose t. T is, let's select t like this, 1 minus 2x squared. So here's the issue over here. We can obviously substitute t, and we can obtain something like this, square root of t. And the issue is that over here we will have x and dx. So how to get rid of x and dx? Well, let's try to differentiate this expression with respect to x. Consequently, let's write dt over dx is, let's see, it's obviously minus 4x. From this equation, we can obtain that dt is actually equal to minus 4x dx, or from this equation we actually obtain that x dx is equal to minus 1 over 4 dt. And observe this term over here and look over here. This term appears over here. So instead of x dx, we can write minus 1 over 4 dt, and we got rid of x dx, and we only have dt and a constant. Consequently, our integral will look like this. Minus 1 over 4, and we will have dt over square root of t. Square root of t, or better to say 1 over square root of t, can be written like this. Integral of t to the power minus 1 over 2 dt. Now, let's use this formula to solve this integral. We know that integral of t to the power n dt is, let's see, is t n plus 1 over n plus 1. Let's use that formula. So we have minus 1 over 4 t to the power, n in our case is 1 over 2 with the minus sign. Consequently, we have minus 1 over 2 plus 1 over minus 1 over 2 plus 1. This becomes minus 1 over 4. In the numerator, we have obviously t to the power 1 over 2, and over here we have 1 over 2. Now, this 1 over 2 becomes 2 over here, and consequently we have minus 1 over 4 multiplying 2 multiplying t to the power 1 over 2. And this finally becomes minus 1 over 2 t to the power 1 over 2. The next step is to substitute t from this expression over here. Consequently, our original integral that looks like this, x over square root of 1 minus 2x squared dx is equal to minus 1 over 2, and over here we have, instead of d, 1 minus 2x squared to the power 1 over 2. And that's it. This is the final solution. How can we verify that this is actually the final solution? Well, we can take the first derivative of this function, and I will not do it in this video tutorial. You can do it for your homework. You will actually see that the first derivative of this function is equal to this function, and this solves our problem. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.